Hi, and thank you for coming to my AQ talk. My name is Sarah Almdari. I'm a fifth-year PhD student at the University of Washington in the Fentner Research Group. And today I wanted to present a paper that recently came out in Langmuir, where we used a computational method known as molecular dynamics to study the assembly of a protein known as lysozyme at an interface. So proteins, or nature's building blocks, drive naturally occurring biological processes ranging from sensing or immune response to things like molecular transport and biogenesis. And while we're inspired by these phenomena, more often than not, we don't understand the mechanisms that drive these interactions, which we find to be highly correlated with their biological environment. And that's because many of these processes take place at interfaces like solid surfaces, membranes, or even at interfaces with other biomolecules. Even the world's most powerful spectroscopic and crystallographic methods can't provide an atomistic level of resolution at an interface alone. For example, archives such as the Protein Data Bank contain over 100,000 resolved protein structures, and conversely, very few of these structures have been solved for surface-bound proteins. An air-water interface is one of the simplest representations of an interface in both simulation and the real world, and has really nascent applications. As you might imagine, protein assembly at the air-water interface occurs naturally in many biological processes, which we know is important to their function. However, the factors that control protein self-assembly at the air-water interface and the dynamic processes that occur during adsorption remain underexplored. And that's because proteins are sensitive to characterization techniques and have a tendency to denature easily at interfaces. To date, the interfacial structure of even one of the most widely studied model proteins, lysozyme, at a simple air-water interface has been the subject of great debate in the literature. Lysozyme is a protein extremely common in the body, found in tears, saliva, mucus, and can also be found in egg whites. In applications, it's been a protein of interest because of its high antibacterial and antiviral properties, which can be used in applications of food preservation. However, despite being this widely studied model system, various experimental techniques over the years have supported a variety of different adsorption mechanisms, both denatured and structured, and including generalized head-on, axial, and side-on adsorption mechanisms. Because many experimental methods lack any atomistic insight, determination of interfacial orientation is often characterized by calculating the thickness of the adsorbed monolayer and comparing this to the globular dimensions of the protein. Further, there's been some investigation into the role of concentration, and more interestingly in pH, and its ability to tune self-assembly and therefore control interfacial properties of these proteins at the interface. And while there's exciting preliminary data from methods like neutron reflectometry, these approaches again have low molecular resolution, meaning it remains difficult to resolve this relationship between molecular structure and interfacial properties and function. One experimental spectroscopic method, known as vibrational sum frequency generation, or SFG, is sensitive to changes in biomolecular orientation at interfaces. SFG is a nonlinear technique in which two pulse laser beams with visible and infrared frequencies are overlapped on the sample in both time and space. This generates a third beam that has the sum frequency of the two incoming beams, and this SFG signal can only be generated when centrosymmetry is broken, making it an inherently surface-sensitive approach. Here's an example of a theoretical calculation of two different protein orientations at a simple interface. And we see that whereas methods like Raman and infrared spectroscopy don't pick up on the subtle changes in orientation at an interface, SFG can provide these rich spectra that distinguishes between different vibrational modes at the interface. And although we can generate these rich signals, we still lack this atomistic level of insight into the specific structures or binding domains that contribute to these signals. One way to overcome these limitations is to implement approaches which combine theory, experiment, and simulation. With a prediction of the interfacial structure, we can then calculate theoretical SFG signals for that given orientation or conformation. And then this theoretical prediction can be compared against the signal derived from experiment. And through this method, we can then back out the corresponding interfacial structure. But one question is, how do we get this interfacial structure? And this is where our computational modeling tools come in handy. Molecular dynamics is a method that allows us to simulate the dynamics of biological molecules. In classical MD, the potential energy of a system can be described using a physics-based approach where all the bonded and non-bonded interactions for every atom in the system are defined. For example, the energy of a bond can be described by a simple harmonic potential where the spring constant, or K spring in this case, can be used to tune the interactions between different atom types. And once we have this description of potential energy, we can relate this to force, and integrating force twice gives us the atomistic positions of our system over time, or dynamics. In MD, this is typically referred to as a trajectory, which is just this map of the coordinates over time. And we can use these trajectories to quantify different properties or phenomena that we're interested in observing. So circling back to this problem that I described earlier, we wanted to see if we could provide some clarity in this model system by using a combined theoretical and experimental simulation approach. To accomplish this, we simulated 10 trials of lysozyme at the air-water interface for 100 nanoseconds. And these simulations were initialized with random velocities and orientations near the interface. And through tracking this distance between the center of mass of the protein and the interface, we could track protein adsorption over the course of a 100 nanosecond simulation, which is plotted here in this middle panel. So on the y-axis, we have plotted the protein center of mass distance to the interface, and on the x-axis we have time. And by tracking this, we were able to color in red and blue the trials that didn't adsorb in red, and then the trials that did adsorb to the interface in blue. So just to give you some appreciation of what we get to see in a simulation, here is a trajectory where we're going to watch a protein adsorb to the air-water interface in this semi-stable state. And then shortly here, we'll see the protein unbind, reorient itself, and rebind in a more stable axial pose. And this is where the protein will remain for the rest of the simulation. Some of this jumping that you see across the boundary is due to the fact that we're simulating these systems with periodic boundary conditions. And as you can see here, this protein's finding its final stable state. And there it is. Oops. So next, we were able to monitor the orientation of the protein at the interface by tracking the angle between two vectors. One of these vectors described the length across the protein, and we used another one that described the plane of the interface. And so we'll typically plot this angle as a cosine theta, which is a common way to look at this calculation. So here's a plot representing this analysis that I just described, where on the y-axis, we're describing orientation with that cosine theta value. And on the x-axis, we again have time, where each trial is colored according to the previous plot in red if it didn't adsorb, and in blue if it did adsorb. We can then calculate the probability density of the adsorbed protein being in a specific orientation over the course of 100 nanoseconds. And through this analysis, we see that in the trials where lysozyme adsorbs to the interface, it does so in one of two orientations, given by these two distinct peaks in blue. And by relating this value for orientation back to representative frames from our trajectory, we can then visualize structures which describe these orientations, giving us that atomistic level of resolution. So here I've shown the two corresponding structures, which we've named the head-on or axial interfacial orientations. And I'll just point out that both of these predicted binding poses are bound by the same region on the protein, which we'll discuss in a little bit as well. So while we were fairly confident in the interfacial structures that MD predicted, with the help of our collaborators, we were able to compare a calculated spectra for our MD predicted structure to the experimentally derived signal. And I just wanted to quickly shout out that all of the experimental work I'm about to show was done by Stephen, Thaddeus, and Lars, who are postdocs with Tobias Weidner at Aarhus University in Denmark. So here we've plotted the intensity of two signals in the amide 1 region from experiment, shown here with a dotted line. in green and red. And Stephen was able to calculate spectra for our MD predicted structures, which are plotted using a solid line. And these take into account the thermal fluctuations of the protein at the interfaces. And as you can see, the fit for both of these MD predicted structures is very close to the experimental predictions. And we can quantify this by calculating a residual sum of squares between experiment and theory that further validates this. We then generated a control trial from MD where the MD predicted binding domain was facing away from the interface. And from this, we can see that a theoretical SFG calculation for this control structure gave very poor fit to the experimental signal. And this is both given by a high RSS value, and visually we can also see that this is a poor match. So with this strong agreement, we were able to present a mechanism for interfacial assembly that was consistent across simulation theory and experiment. And now that we had this atomistic information and we were confident in the ability of our simulations to capture important interfacial phenomena, we wanted to explore at least one further point of disagreement related to the role of pH in tuning lysozyme surface orientation. Lysozyme is unique in that it has this isoelectric point of around 11, and it's also composed of a highly hydrophobic globular core, meaning that the protein is slightly basic and carries many of these charged residues on the exterior of the protein. And based on these interfacial orientations that we determined earlier, we were able to characterize the residues facing the air-water interface as depicted here through two different binding domains. The primary binding domain is the set of interfacial bound residues, which is shared across both the axial and head-on poses. Whereas the secondary domain was this domain that we predicted to be critical for maintaining an axial pose at the interface. And this was done by generally looking at the orientation of the residues that were positioned towards the interface. And we specifically saw in this region that we saw both hydrophobic and some charged residues. More interestingly, we noticed the presence of many lysine residues in and near the secondary binding domain. Lysine is particularly interesting to us as it carries a pKa of around 10, meaning that these exterior lysine residues become neutral near the isoelectric point of lysozyme. And we predicted that this would increase the affinity of this domain towards the air-water interface. So to test this, we ran an additional set of simulations, taking the adsorb trials that we ran at pH 7, and we reran them at pH 11. pH in these simulations is only represented by a change in the charge of residues and not by adjusting the ionic concentration. So here I'm showing those same results that we talked about earlier, which were conducted at pH 7. And when we do the same analysis for the simulations at pH 11, we see a shift in the orientation of lysozyme, where the adsorb trials are mainly in this head-on and axial pose. We see that the pH 11 simulations shift into this side-on pose. And when we looked at representative structures for this side-on pose, we confirmed that this was indeed due to the additional binding of lysine in the secondary domain, allowing exposed regions of this hydrophobic core to bind more closely to the interface. And so with this insight, we were able to close the loop on pH-controlled self-assembly of lysozyme at the air-water interface. And this is an exciting example of how simulations can help lead and augment new experiments, especially in these data-poor, low-resolution fields of study, such as structure-function relationships of proteins at interfaces. Here specifically, we were able to probe at very high resolution and very small length scales, validating some of these early predictions from literature. And so to conclude, just to summarize what we've talked about today, I've showed a combined theoretical and experimental approach that provides a mechanism for interfacial adsorption with high confidence. We've also shown that simulations can be used to predict the interfacial orientation of proteins with high accuracy. And we've demonstrated an example where simulations were used to augment these data-poor fields of studies, resolving discrepancies surrounding interfacial orientation. And with that, I would like to acknowledge our experimental collaborators, Stephen, Thaddeus, and Lars, and Tobias, who are at Aarhus University. We couldn't have done this work without them. as well as all the members of the Fentner Research Group who have been so helpful during these virtual times. And thank you. Oh, and our funding sources. And thank you. And if you have any questions, I'd be happy to answer them at the live Q&A, or feel free to shoot me an email or tweet.